The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so let's get started. A recap. You should be all pleased you have learned a lot. We covered the quantum, solid state, and the statistical physics. This is my lecture 11. Okay. And so what we learned, first, the quantum and the solid state gives us the energy levels and the energy state. What is the quantum state? And statistics give us at the equilibrium, each quantum state, how many particles, photons, electrons, photons. And going back to counting the state degeneracy, we get the density of states. So at a certain energy level per unit energy interval or per unit wave vector, how many quantum states we have. So with that, you can do the counting. And this is F times D gives me a number of particles near that energy per energy interval. If you integrate, that should give you the total number of particles, electrons, photons. Or if you multiply by the energy of a particle, that gives you the energy. Or if you multiply by charge, it gives you the charge density. If you multiply by the momentum, it gives you momentum, right? So with that, you can start doing for example, the energy stored, specific heat, etc. And then we said at the end of last lecture, we're moving on to look at the transport. And the first idea we look at is, if I want to find out how much energy is going from point 1 to point 2 into different space, and what I'm going to find out is what's the transmittance. So if I have a particle or wave, now I don't know how to call them, right? It's particle-wave duality. And so if I have a carrier, right, electron, photon launch from point 1, and the transmittance is how many of them will reach point 2, right? That's give me the fraction, right? And then say if I know the velocity, then I know the flux from point 1 to point 2, which is the velocity in that direction, transmittance. And if I want to find the energy flux, that's per, this is how much energy I have starting from that point, right? So this is where we're going. In the coming chapter, we're going to focus on using the wave picture to deal with this transmittance. And then if I want to find the net flux, if you recall in chapter 1, when we derive Fourier law, we say it's from 1 to 2 and minus 2 to 1. The difference give me the net flux, right? So what we're emphasizing so far is you know how to do the counting. And our focus in this chapter is talking about the wave picture, right? We've been using the wave, Schrodinger equation for atoms, electrons, and all wave picture. And why we have to look at the wave, and this is important if I deal with the interface. Because I mentioned before, ideal interface is zero thickness, right? It's compared to wavelengths. If that, say, very small compared to wavelengths, then I should use the wave picture. And so here is the magnitude, order of magnitude of those wavelengths, right? Black body radiation, Wien's displacement, or say wavelengths times temperature is about 3,000 micron Kelvin. So at room temperature, that's 10 micron. It's a very large distance, 10 micron compared to a zero thickness interface. Right, so if I have a flat interface, I need to consider the wave optics. So even for thermal radiation, and electrons, here are two different pictures. If I look at the electron in metal, the Fermi level is within the band. And corresponding to this Fermi level, those are the electrons that moves. Near Fermi level are the electrons that moves, right? And the corresponding wavelength is within the bands, right? This is 0, this is pi over A, Brillouin zone. So if it's half, that's wavelength is about 2A. Okay? Say of the order of a few lattice constant, that's the electron wavelength in metal there. And if I look at the semiconductors, right, if I say this is the valence band, and most of the electron is at bottom of the valence band. So that's near k equals 0. And those electrons could have very long wavelengths. And in fact, say in the last lecture, we talked about the de Broglie wavelength. So that's the thermal, if I have a thermal energy, kT of the, say, average energy is kT of the electron kinetic energy. What's the corresponding wavelength? That's the de Broglie wavelength, right? So the last lecture, we got the h squared and 2 pi mkBT. So if I substitute my numbers, this is h is 6.6 10 to the minus 34 joule second, right? This is h. And in the denominator, I have 2 pi. If I think about electron mass, right? 9.1 10 to the minus 31. And Kb is 1.38 10 to the minus 23. And 300 Kelvin square root. You go to do that, you get this number. I get about 40 angstrom. So it gives you the sort of average wavelength of those electrons with that energy kT near the bottom of the conduction band, right? So again, this is 40 angstrom seems awfully small, but we said before the sharp interface is 0 thickness, and in fact you can deposit the layers almost atomically flat, right? So I again say, if in those cases you should consider the wave reflection transmission just as optical waves. And photons, this is the dispersion we learned before, typical one. And of course, at the zone boundary, the wavelength is 2A, right? And it goes for a very long wavelength. This is the sound waves. If you have a solid, you log it, you'll hear it. It's a very long wavelength at the zone center to the whole, just 2A in between the lattice constant, right? And if you do your, like a black body for photon, you do your density of states. You remember when we do black body radiation, we do energy of photon times density of states times the Bose-Einstein distribution. That's how we get black body radiation. And you do the same for photon. You'll say it's similar to black body the spectrum, except you're cut off. You have a cut off wavelength because it's unlike electromagnetic wave in free space. That one goes very small, right? So the lattice constant, 2A lattice constant. So overall, it's good if we start with thinking, when I calculate the transmission, next I will consider one single interface. If I have 1, 2, and I have those waves, this could be electron wave, could be photon wave, and could be photon wave comes to the interface, and they will be reflected, and they will also could be transmitting across the interface. How I can calculate how much is reflected, how much transmitted, right? So that's my first order of business, and that will give me the transmission from one side of interface to the other side of interface, right? And of course, I could have layers, or I could have many layers, right? This is, I'm considering really a planar geometry, make a 1D problem simpler, right? So in this case, 1 and 2 and 3 will have multi-layers coating when I use optical coatings. right? How I will calculate the transmission and reflection. And turns out the waves are very similar, whether it's an electron wave, or photon wave, or electromagnetic wave. You'll see the behavior are very similar, although at the quantum level, we know that electron, photon, photons are different, right? But the general wave behavior in terms of interference, in terms of diffraction, in terms of tunneling, all those exist for all waves. And there are different technologies developed based on this phenomenon. So let's look at, start with a plane wave at one interface, right? Let's just consider the simplest plane wave. And the reflection at the interface. You can see here, I'm not even distinguishing whether it's electron, electromagnetic, although my detailed derivation will have to start with different wave equations, right? And in this case, I want to actually start with a quantum wave, or electron. And that's because that's the simplest. Electron, if you think about Schrodinger equation, in certain sense, it's simple because it's scalar. The wave function is scalar. It's not a vector. When I go to acoustic waves, right, the lattice vibration, there are 3 polarization, 2 transverse, 1 longitudinal. Electromagnetic wave is a vector wave. The electric field is perpendicular to the direction of propagation. There are 2 polarization. So I will start with the simplest electron wave. It's a scalar. Right, and we have done the electron wave Schrodinger equation before, 2m d psi. Let me think about the 1 electron, 1d dx squared plus U minus E. This is the steady state part, right? U minus E, U is the potential, E is the electron energy. And of course, there is a time-dependent part. That's the, remember, the time-dependent part is just exponential minus I omega t, or this omega equals E over h bar. That's the Planck relation, right? And for this wave, we solved it before. It's a simple second order differential equation with constant coefficient. So we solved this before, and then let me write it down. The general waveform, as if I combine the time and the space dependent all together, that looks more like a wave, plane wave, I omega t minus k x plus b e minus I omega t plus kx. I have 2 solutions, right? That's what we written down before. Now, you can tell me the first solution is the wave propagating in which direction? Positive x. Second wave is the negative x direction, right? Those are the 2 counter-propagating waves, and it's a superposition of 2 waves. Now I'm going to look at if I deposit a film with the interface, right? So this interface, I look at the 1D. So forget about the, say, YZ direction. And so 1D interface, this is one side of the film. This is the other side of the film. And this is typically if you put 2 different semiconductors together, right? And here is a conduction band EC1. Here is a conduction band EC2, right? So EC1, EC2. And at the interface, there's a discontinuity of the energy of the electrons, right? And the difference here is U, or delta. The different places have different symbols. And this is typically called a heterojunction. When I put two different conductors together, semiconductor together, at the interface, there's a potential barrier, electrical potential barrier. And the detail is more complicated than I draw. I draw a sharp one, and in fact, the electron here is not stable. It's going to fall into here, so it's not going to be as flat as I'm drawing here. Here's a very simple approximation. Okay? And now I have an electron wave comes in. So I can take a form of the incident wave. And if this is my x direction, at the interface, there will be reflection. The wave will go back, right? On the other side, there could be transmission. The wave can go over the barrier, continue, right? So I have reflection, I have transmission. I want to find how much reflected, how much transmitted. Okay, so here you can use the plane wave solution. For medium 1, let me take this U as a reference. This is 0. Here is so electron here experience a difference between 0 and magnitude U, right? So because of this, my k in each region, in region, let's say here is my 0 origin of my coordinate, and you can always take your origin. But typically, it's much easier if you set the origin at the interface, at least at the first interface. If you have multi-layers, you have to continue because there's distance from 0, so you count that distance, right? So if I put this one at 0, I have incident wave psi I, right? This is the incident, and has an amplitude A, and going to the right-hand side, so exponential mass I, omega t minus k1x, because this is region 1, and this is region 2, right? My k is different because here, my k, if you look at this, is 2m E minus U divided by h bar squared. You combine this together and reverse the sign, E minus U, not U minus E. Okay? So in this region, U equals 0. So whatever energy E of the electron, mass potential 0. So that's the waveform, the wave vector of K1, right? And they reflected here, psi, this one, this is reflective wave. You can see the reflective wave is going backward, right? My coefficient is on B, I say. I want to find out the reflection A and the B relation. My transmitted wave in region 2, so if I write down the transmitted wave is say exponential, again it's forward propagating into x direction, positive x direction, right? So it's say mass I omega t mass k2x, not k1x. And this k2, you can say is 2 m E minus U now, h squared. And the K1 is just U is 0, so it's 2m. E is the energy of the electron, 2m over E, 2m E over h squared. Right? So this is the difference of these waves. Here in region 1, they reflect, incident reflected, they differ only by here is plus, here is minus. Coefficients of the course are different. And transmitted wave in region 2, the coefficient is different, wave vector is different. Two difference. Right? So I want to find out relation between 1 and 2. And to find this relation, I have to use the interface condition. Right? At the interface, the wave function is continuous. The derivative of the wave function is continuous. So the wave function So it's not just a one wave function. When I say wave function, it's all the waves, you add them all together, right? You add the waves together. And so at the x equals 0, what I have is psi I plus psi r. On the left-hand side, I have two waves, incident, reflected, right? X equal to 0 equals cosine t, x equal to 0. What I get? So the incident is A, x equal to 0, so k1 x, that's 0. Minus I omega t is shared the same. Omega is the energy of the particle, right? E divided by h is the same on both sides. So when you go, the wave go from one media into the other media, the frequency doesn't change. Okay? And so what I have here is really A plus B equals C. Right? Because E minus I omega t, E minus I omega t, and cosine t is E minus I omega t, that all cancel. Right? X equals 0. So I have that. My second condition is a derivative. So it's a total derivative of all the waves, and because the summation, so I put each one. So I first take derivative. You have to be careful. You first take derivative, you set x equal to 0. And this equals derivative x equal to 0. So if you take a derivative, so you say with respect to x, so this is a ik, right? Negative, negative. So I have positive ik1 a, that's the first term. That's the incident. Reflected is b. And here is minus I times plus k. So I have a sign change after I take derivative, right? So A minus B equals IK2 times C. So that's the application of the two boundary conditions. Yes, Ron?
If they were to be different refractive indices, would the frequency change as the wave goes through, or just the...
No, the frequency doesn't change.
Oh, okay.
Right? When you have light goes from one media into another media, the frequency does not change, the wavelengths change. Okay? So this is a k is my, you remember hk gives me a momentum, p equals hk over, say h bar over lambda give me the momentum, right? So here is my two conditions. And I want to find the ratio because I want to find transmission is C over A, reflection is B over A. So I have two equations. I want to find the ratio. I can find those ratios. And the ratio I have is, so based on this, I have a C over A is 2K1, K1 plus K2. And the B over A is K1 minus K2, K1 plus K2. So those are my solutions for the coefficients for the transmitted wave and reflected wave relative to the incident wave. Right? But what does this coefficient really doesn't mean anything yet, because we said before the wave function is not a measurable quantity, right? In quantum is the psi times psi complex conjugate that gives the particles, right? And the particle flux in quantum right? The flux of the particle, we give this expression before, is in the vector form is I h bar 2m, and psi complex conjugate of gradient of psi, and psi complex conjugate times gradient of psi. So that's the particle flux. And another way to write this, if you use a shorthand, this is a real part of I h bar and m psi complex conjugate of gradient. Because this one is complex conjugate of this one, so the difference gives overall is the real part of this. Okay? And now I'm going to plug in, because I want to say what's my, for example, if my incident, if psi is my psi I, right? You say psi I is A exponential minus I omega t minus kx. Okay, so let's substitute in. So in this case, the incident flux is a real part of I h bar to m. Psi is A exponential minus I omega t minus k1x. That's the incident. So the derivative is d psi. I first take complex conjugate, and then I take the derivative. And complex conjugate, this one becomes plus, because of I, right? Minus I becomes plus I. And k1, I'm going to take a more uniform, I say it's complex, because omega is a frequency. With vector, I'm going to also say it could be real and imaginary or complex number. I treat it. So in that case, I have, if I take a derivative, I should have plus, that's I, and this is times minus complex conjugate k1 and exponential plus omega t minus k1 x. And right? So I have a A. I should have a A here. A complex conjugate. Okay. And minus I omega t plus I omega t cancel. Time is not there, right? And k1x plus I k1x. Here I should be complex conjugate in general, right? Because I first take a complex conjugate of this function. And so in general, this one may not be 0 because this k1 and plus k complex conjugate, they may not cancel if it's an imaginary number, right? For my case here, because in region 1, U is 0, so this one is real. Doesn't matter. And also either x equals 0, right? This also goes out. So at the end is J1, at least I can say at the x equals 0, you can say this is a squared, A times A complex conjugate, I times I is -1, another negative, right? So that's a positive. So I really have this I cancel. I have A, M, H, and K1. So J1 equals H, M, and K1, A squared. Okay? So this is my particle flux, incident flux. And similarly, the reflective flux is also, if you substitute in, it's the same as HK1 M B squared, right? But the transmitted flux, I have to be careful. Okay? The reason I have to be careful is you can say my solution, if energy is less than U, K2 is imaginary. Okay? So in that case, I have to be really carrying that real part of K2 complex conjugate, because this is a complex conjugate K2 and the real part of that. That's where I have to be careful. Okay. So based on this, I will define the reflectance and transmittance. Sometimes I use reflectivity. Sometimes I use reflectance. And the difference is most people don't distinguish it. Reflectivity is more intrinsic. So if you have a most ideal case, that's an intrinsic surface property. And reflectance is extrinsic. If your surface become changed or rough, then there's a different value. So this is a more rigorous way of calling it, but you can, most of the time people don't care. So reflectivity for here might have an idea is JR divided by JI, and because K1 cancel in the same media, so reflected, transmitted, so it really just has B squared over A squared. And B squared over A squared, if you say B over A, so I have K1 minus K2 and K1 plus K2 squared. So that's the reflectance at the interface for a particle wave due to quantum reflection, right? And transmittance or transmittivity and there's also transmittance. And in the transmittance, I use tau equals JT over JI. And here it's different because J transmitted is a real part of K2 complex conjugate over K1 is real anyway. And here I have C squared over A squared. And this is a real part of K2 complex conjugate K1. And C squared over A squared, you can say it is K1 plus K2 and 2K1 squared. Right? That's my transmittance. Okay. Now, because I carry this real part, right, I should really look at the scenario, different scenario, when energy is larger than U. If energy is larger than U, K2 is K2. If you look at the K2, is 2m minus U. That's real, right? The energy of the electron is larger than the barrier height. That's real. Okay, and in that case, real. So it's I can forget about this. You can see this becomes a 4K1 times K2 divided by K1 plus K2 squared. Okay, so in this case, I have tau is not 0, but it's say R is not 1. Right? I have quantum reflection. Even I threw an electron, even you normally think an electron as a particle, when it comes to an interface, it has reflection. Right? Even if the energy is higher than the barrier height. So now you just say, next time you throw a ball over the wall, there's a finite probability bounce back, even you throw it higher than the wall. It's quantum world, right? Okay? And so that's your first case. And your second case is E less than U, right? E is less than U. If you look at here, your K2 is imaginary, right? K2 is imaginary, and the real part, that's 0. So if the energy of the electron is less than the barrier height, U, your transmittance is 0. And your reflectance, if you plug in here, this is real, this is imaginary, this is real, this is imaginary. The modulus is 1. Right? So reflectance is 1. So the particle is all reflected. It's expected, right? You throw a ball below the wall, the particle, the ball bounces back. But there's still something special. Okay? You look at the other side of the wall, there is a finite wave of the ball. Right? That's because if you look at the transmittant, so also the transmittant, there's no real particle go through the wall, the barrier, right? But the wave is now 0 because here is my wave. Phi t minus I omega t, K2 is imaginary, right? K2 is imaginary, so imaginary times imaginary, real. It's negative real, so it's a negative exponential decay function. So in this case, what I have is, this is the ball coming in, the particle comes in, and there is a finite wave on the other side of the interface. The average speaking, there's no particle go into the other side, but the wave function is now 0 on the other side, right? And this wave is called evanescent wave. Evanescent. Okay? And now, what's the magnitude of those? Right? So if you look at your decay of this evanescent wave, if you look at decay of evanescent wave, is really the magnitude E minus U 2m h bar squared. That's the square root. This is really the magnitude. So what I have here, the magnitude of K is 2m really E minus U and h bar squared. That's by the K2. That's the decay, right? Or U minus E, right? So if I look at the electron U mass E, let's say take a 1 electron volt. So the energy, so what's the order of magnitude? Is 2 times 9.1 10 to the minus 31. And electron volts, 1 electron volts is 1.6 10 to the minus 19. And h bar squared, h bar is 1 10 to the minus 34, so 68, right? So this one is 31, 19 gives me 50, right? And this gives me 68, so that's 18. 18 square root is of the order of line, right? And the rest is okay. Here maybe I have 5. Order of line inverse meter. Okay? So that's the magnitude of this wave extend if it's an electron into the other side. Is of the order inverse of that. Gives me what? 2 angstroms? Right? So it's a evanescent rapid decay, exponential rapid decay wave on the other side. You say, who cares 2 angstroms, right? But let me tell you a story. So there was this guy, he just finished his PhD and went to a job interview at IBM Zurich. And his name is Binish. And the interviewer asked him, say they want to measure the surface roughness of say to very high precision, asking him whether he had ideas or not. And he thought about this and came up with the idea that's using a metal tip, and this is a metal surface, right? And he put a bias, so vacuum here. There's an energy level. That's you read the Einstein work function. Maybe you didn't read you read the nature, the wave nature, the particle nature of light. But say there is a few electron volts gap here, the barrier, vacuum, right? Work function of metal. So here is a few electron volts, and he say if you bias it with a voltage, right? The electron exponential decay, but once they meet the other metal, become alive again. We'll talk about that. That's a tunneling of this everlasting wave. And it's very sensitive to atomic scale bumpless, right? Because this is Armstrong level, exponential. So with that, you can measure, that's the principle of scanning tunnel microscope. You really can measure the electron wave function on the surface. So you can actually image atoms. And so we got a Nobel Prize for that. Okay. Hopefully you'll get a chance when you have an interview like that. You have to think. You have to be able to come up with an idea, right? So that's the quantum world. It's going up a hill. Now you reverse it. You say, what if my electron is going backwards from here to here? Is there a reflection? You look at the derivation, there's no difference. Even you go downhill, even if you not go barrier, you go a step down, you still have a reflection. Right? You have discontinuity in potential, you have reflection there. Okay? So, this is in fact, this is a Lomer incidence, right? And when you consider actually electrical interface resistance, for example, right, electron can actually come to an interface not just a Lomer, it can come all directions. And you should be able to sit there and do any angle in incidence, right? In fact, I checked a lot of electrical engineering book. Nobody even did that. I was surprised. Okay, if you're an electrical engineer, you should do this. Okay. So this is for electron wave. And now let's go. We say this is scalar wave. It's the easiest. And let's go to more complicated. And let's look at the vector wave. And vector wave, the less complicated vector wave is the electromagnetic wave, right? EM waves. It's quite a big leap from a Schrodinger equation, which is a scalar equation, which is by no means easy to solve. We got multiple electrons, so there are actually no good tool to solve that right now. Even if you have 2 or 3 electrons, their mutual interaction becomes very difficult to solve. And that's a many-body problem. But say, let's go to do EM waves. And for that, you have to go to Maxwell equations, right? And even you forgot it, but you heard about it. So let's rewrite the Maxwell equations. And we have 4 equations. E cross H minus time derivative. The cross E and cross H is d dt plus the current, and we have then the divergence of the displacement field equals the charge density, and the magnetic divergent magnetic induction is 0. And just to review, this is essentially what the first equation say. If you change the magnetic field, you have a general electric field. The second, if you pass a current through a coil, right, you generate magnetic field. And this is the Faraday law. This is more like an Ampere's law, right? Some of the high school experiment. And Maxwell only added one term. And he got all the credit. Okay? So what do we have here? E is the electric field, right? The electric field is the gradient of electrostatic potential. And so the unit is volt per meter, right? And H is a magnetic field. And sometimes I don't remember the unit, so I go back to think of this. Current density I know, right? Current density is, here is amp per meter square. So here is the, say, times 1 meter, that gives me magnetic field is amp per meter, right? So magnetic field is amp per meter. And D is the electrical displacement. And what it means is if you have a material, right, you have atoms. Atoms has electrons, ions, right? If you have an electric field comes in, you know that they will get polarized, right? Positive charge has a force along the field direction, negative charge opposite field direction, right? So that means they will have a dipole. So you'll have, in this case, you have more like a dipole. Here is a positive, here is a negative. Okay? Right? So D is the polarization per unit volume, dipole moment per unit volume, and plus if you have original field comes in converted into the same unit, right? So that's epsilon 0, that's a vacuum, plus the polarization per unit, the dipole moment per unit volume. So dipole moment is the dipole moment is the charge times meter, and per unit volume is cubic, right? So the unit here is Coulomb per meter square. Okay? And from Coulomb per meter square, this is Coulomb per meter square, you find the epsilon 0. That's the vacuum permittivity. I would say permittivity. Permittivity, epsilon 0 is 8.8, 10 to the minus 12. And here is should be Coulomb epsilon here. Is a farad per meter. Okay. So I have this one is a farad per meter. Okay. So I have the this is a D here, the displacement field. I said that this is the one external field create a dipole, right? In a real solid, it's not that simple because you have an atom here, you have another atom here, right? You have adjacent atoms. And not only the outside field, but also the Lex labor, the dipole itself will affect the atom itself. So it's actually a summation of all this effect, okay? And this one, this is a non-movable charge. This is the charge attached to the atom. Okay, that's dielectric, right? So we sometimes write the epsilon r, and times E. Well, this combined together gives me another epsilon. That's the dielectric function of the material. It's not a constant. Sometimes we call dielectric constant. It's not a constant. It's a function of wavelength. It's a function of frequency. Okay? So that's the displacement. And similarly, magnetic induction B, you can write as epsilon vacuum, mu vacuum, mu r, and times H. Right? This is just like we write into the displacement field is the electric field times the dielectric constant. And here is the vacuum permittivity, the relative to vacuum. Most materials at a high visible wavelength or high frequency, this one is about 1. It doesn't have magnetic response, most materials. Right? At a low frequency, you have magnet. But say high frequency, most materials don't have the magnetic response. And in fact, that was the basis of an invention made by Professor Marian Sojcik, right? He was trying to think about how do you get a powerless, wireless, coreless power transfer. And the problem is, if you want to beam a lot of power through this space, we will all be cooked. We have dielectric response, right? Microwave, you heat it up. But say, because materials at high frequency don't have magnetic response, so he thought about using magnetic field to deliver the power. So you have to start up trying to commercialize that. Okay, so that's the basic equations, and a few more comments. The relation between current, when that's a real current, a free electron, the current flow, right? And current, of course, is related to electric field through if you have a conductor or semiconductor, that's the Ohm's law. So J equals electric conductivity, that's Ohm's law, right? Electric conductivity is sigma. And here the unit is inverse Ohm Siemens meter, right? Ohm centimeter, yeah, inverse. No, should be inverse. Or say inverse ohm is also Siemens per meter, different units. If you don't use it often, it's very confusing. Okay, so we have all these quantities. And further, what is epsilon, say the charge density? Right? And this charge density is the lead charge per unit volume in the material. Okay, so if you have a semiconductor, right? In a semiconductor, you can have a positive donor, right? When, say, if you put a phosphor there. Okay, so let's say put a phosphor atom in silicon, and phosphor atom loses the electron. So the atom itself is mobile, electron becomes mobile, right? So what you need is this is a positive charge. You also have an electron negative charge. You add them all together. That's per unit volume, how much charge you have. So these are the set of equations describing the electromagnetic waves. And now we can say why. Let's do a few math operation. Just get familiar with it. You have seen them. So if I look at this, I can eliminate. I will first eliminate because B right? Here I can write as mu h, mu 0 times mu r is mu, and permittivity. And so B equals mu h, so I use the first one. I get the first equation, delta cross E equals minus d mu h dt. That's the first equation. And the second equation, I have delta cross h equals d dt and epsilon times E. This is the dielectric function, which is epsilon 0 times epsilon r, right? The displacement field, and plus sigma times E. Those are the, if I use constitutive relations and eliminate B and D, I got the equation here, right? And let me first drop this term. Okay, let's consider dielectric. There's no free charge in the material, so electric conductivity is 0. Okay, with that I can plug this h into here, right? And I take a time derivative on both sides, and then I get a dh. So this is assuming mu and epsilon are independent of time, right? And if it depends on time, you have to be careful. It's not mine, right? Sorry. Oh, okay. So if I have the so if I eliminate if I take this epsilon mu out, I'll be independent of time. And sometimes you have to be careful, because when you do those kind of mathematical operations, you make assumptions, you may lose big opportunities. Okay? And this electromagnetic field is, there are a lot of new concepts that is all based on going back to the original equation and relook at them and see where are they, say if you say under, where are the approximations made. Okay, you were reading Yablowitch chapter, say paper on photonic crystal, right? And one of, say, his photonic crystal is really that the concept in that case, the epsilon, which we typically take a uniform, right? But say he was really taking this epsilon as a periodic function. So he put the epsilon as a periodic function, and that's like a periodic potential for atoms. Right? If you think about when we solve the band gap of electrons for Schrodinger equation, that come from the fact that the potential for electrons is periodic, right? The Maxwell equation itself, there's say no potential here, right? It's really, he put this one epsilon as constant, and he was really using the analogy, and in fact, say I spent one day I was in Berlin. We both of us were wandering in the city, so I was talking to him. He said when he conceived the concept of photonic crystal, he wrote a paper. So photonic crystal, what is a photonic crystal? Is basically periodic arrangement of whatever glass beads. You can think about that, right? And it's if you look at the evolution in bulk crystal, we have band gap, and in the 70s, there is this concept of superlattice, quantum wells, right? You read again Isake and Tsu paper, and that's putting multi-layers of thin films, right? That makes the one dimension, you got the artificial, this is what we draw the potential, periodic potential. That's the chronic panic model we talked before, but it's artificial material, right? So you go from a 3-dimensional crystal periodic potential to 1D. And that's a big jump in concept because it's artificial quantum structures, right? And on the other hand, in optics, you have the form, the latter. Over 100 years, people know how to do coating. People have been doing refining optics. They code multi-layer films, right? Some of this is purely, say, anti-reflection or purely reflecting the purpose. And so the reason, so you have those multi-layer thin film coatings, which is typically of the order of like quarter wavelengths. And you can code it so that it's complete reflecting. What does complete reflection is the wave function of electromagnetic wave with 0 inside. That's a forbidden. It's a band gap in 1D, right? So what Yablowitz proposed photonic crystal is how to make this back into 3D. What LaSure has is electron photons in 3D, and researchers we have created this 1D structure, right? So that's you see is the opposite direction going. And here is trying to make photonic analogy of thin film to 3D. Okay, so he said that when he wrote the paper, you go to read his paper, and there's no math inside, right? He was just a concept. And he submitted the paper, and he know who he wants to be reviewer. And his friend said, "Do you really want to publish this paper?" This is really doesn't look like a paper. It doesn't matter, just publish it. So that's what you read. Okay, it's the beginning of a new field, photonic crystal. Okay. So that's epsilon is a function of R, periodic, right? And your epsilon could also be a function of time. In fact, I was doing some when I did my graduate school study, right? I never came up with big ideas, but once I was writing down the loads, I said, okay, because I was doing some stuff during the optical, say, fast laser material interaction. I say, during that process, the epsilon will change as a function of temperature, and temperature changes as a function of time. So I have to keep data there. I wrote all those equations. And a few years later, my friend asked me, I said, actually, it's in my notes. But it never got anywhere. So, one story. But anyway, let's continue here. I have two equations. I drop this. I'm going to eliminate, I say, mu epsilon constant. And I'm going to then put it out. And I can eliminate h. And what I have here then is the equation. So if I eliminate h, I have delta cross E over mu. And here I have epsilon. I start to get a wave equation. Okay? And you can use the vector operation to rewrite this into if you use a vector relation, you will get actually there's a negative sign in the front, and delta epsilon square mu epsilon dE dt square. And if I continue to carry that, it will be mu sigma dE dt. Okay, this is the one I carry the metal term, the conductivity term. If I don't, I have a pure wave equation. If I drop this, you can see this is a wave equation, second order in space, second order in time. Unlike the Schrodinger equation, which is the first order in time but has an imaginary number in the front. Now I have a real wave equation is the second order in both space and time. Right? So this is the Maxwell equation. And if you look at the typical wave solution, plane wave, epsilon is a function of r and t. And this is a vector, so that's the polarization direction, the electric field direction. And this is the propagation direction, omega t minus k dot r. So this is a plane wave expression we talked before. And you substitute back into here, you will see it satisfies the wave equation. Right? And in fact, if you do it, if you substitute it back, see this left-hand side is the second order derivative in space, so I'll get a k squared. So I will get a k dot k, right? And the right-hand side, I will get a mu omega squared, this is time, and epsilon plus I sigma and omega. This is this term combined with the first term. And the rest, I omega t, that this term cancel, the phase factor will cancel. Okay? And this way, I can write the expression as, because of omega square, so I have mu epsilon tilde omega square. The wave vector is proportional to omega. For wave in free space, this is epsilon 0, mu 0, free space, right? And this is what the triumph of electromagnetic wave, because we predict, Maxwell equation predicted the speed of light. Okay? Because when you do this, you get the magnitude k squared equals omega divided by, here I do the square root of epsilon tilde mu, and this one we can write it into so I can write it k, the magnitude, this is not square, the magnitude. So the magnitude of k equals omega times c, right? Ck, omega equals ck, that's the dispersion. And c is square root of epsilon tilde and mu. And typically we define refractive index as the speed of light in vacuum divided by speed of light in the medium, right? And the speed of light in vacuum, this is epsilon 0, mu 0, and it's approximated because I say most high frequency magnetic response is 1, so this is a epsilon tilde over epsilon 0, and this one is epsilon r. So even for metals, right, very often we don't tabulate these two separately. We just tabulate them together into epsilon r, the relative dielectric constant. Okay. So there are a few interesting stories here again. Okay? You take a positive square root going from here to here. You take a square root, and you see that's a lecture solution, right? And if you go to look at your Maxwell equation, it turns out that this wave, it's a right-hand wave. So you go, say, this is epsilon E direction, electric field direction, right? It's a transverse wave. This is what the equation tells you. You check. Right? It's a transverse wave, so electric field will be perpendicular to magnetic field, will be perpendicular to k, the wave vector direction k, the wave propagation direction. That's why it's a transverse wave, right? It's not only transverse wave, it's also right-hand wave. What the right-hand mean is, if you recall when you learn, let's say is E cross H goes to the wave propagation direction, right? So is the right-hand side, your E direction, you grab to the H direction, the thumb point to the K direction, okay? So it's a right-hand wave, it's a transverse wave, except say we ignore the possibility of when you take this K square root, it could be a negative also root solution, right? Negative solution typically are ruled out, but if when epsilon and mu could be negative, right? When both of them could be negative, it turns out that you go back to check the equation again, you have to take a negative root. So this effect was predicted in 1950s by Russian scientist Versanago, and his paper was forgotten. Okay, but in 90s, people start to pay attention to it. First, there are natural materials with epsilon negative. It just doesn't have natural material with mu equal negative. Why the natural material could have epsilon negative? Epsilon, remember, is a response of the material. I think I erased it. When you have electric field, the material will polarize, right? If it's an electron, for example, and then when you have an external wave comes in oscillating, the electron create a resisting, say, direction field. And if that field is larger than the incident, you get a negative direction displacement. So the epsilon becomes negative. But there's no material with mu negative. Then say in 90s, people designed this artificial resonator structure that generate say artificial magnetic. So you basically create a loop with a gap, and then when the electric current oscillate in this loop, they generate magnetic field. And when you make it very small, the magnetic field could be very, very fast, make it smaller, right? And if you bring both epsilon and mu negative in the same frequency range, you have to go to take that negative root. So become a left-hand material. So E cross H, K goes the other way. So this is a K go this way, but energy go this way. A lot of confusion at the beginning, because whether there is this possible or not. If you check the literature, this is called metamaterial. Okay, it's not the metal materials, MA, not the ME. Okay, and it was an interesting story, many interesting stories. But some people say metal material. So we study metals, but it's not a metal material. It's a metal, and it's really artificially designed material, so it has strange properties. And one of those first achievement is design material in microwave range, so that to prove that the refractive index really should be taking a negative value. So that's really, later on you'll say, it's pretty strange, because when we think about optical light refraction, right, this is the refraction, Snell law. We'll talk next to Snell law, right? But when the N is negative, the refraction actually happens this way. And it's pretty weird. So it's still a very active field. And you heard Harry Potter story, the clocking, right? So in that case, what happens is it could be solution of Maxwell equation comes in here. You have object. And this actually will be easy for fluid mechanics if you look at fluid mechanics, right? And in small Reynolds number flow, you go this way, right? So what it means, the Maxwell solution like this means is even you have an object here, if you're away, you don't see far away, there's no scatter light, right? So what do you see? The light goes around, but say you look at it, it's just like the object doesn't exist. That's what's some of the strange effect of those metal materials. Okay, and I think I'll stop here, but let's look at now you can see a lot of interesting stuff. It's no longer. So if you go to check, say this at the beginning, there are a lot of papers. There are papers say there's no negative refraction. Basically, this is a little bit confusing because the energy is propagating forward, and information is propagating backwards. Typically, people like to associate wave vector to information, and there's a lot of debate in literature. But now I think the debate is all gone, and it's very active. In fact, so I just mentioned that epsilon could be negative. When epsilon negative, there is also, it turns out that again, all this is, we're going to talk more next lecture. There is a surface wave. We just said the evanescent wave is an exponential decay on one side, right? We just say the electron evanescent wave. You have photon evanescent wave. But say this, when epsilon is negative, you could have a surface wave that decays on both sides. Doesn't exist far away from the interface, so it's only confined to the surface. And that's the surface plasmons when these are the electron. So let's say, let me just do a few photon. No, I'll go to this image. Okay. So though you can say that this is a really periodic structure in 3D or 2D. Originally, it's like films, as I said, right? In fact, I was at the UCLA, Yablowitz was UCLA. I remember once I attended a student thesis meeting. There was another professor just say, "There's no Bragg photonic crystal. It's just a Bragg reflector. Bragg reflector is the 1D structure. People call Bragg reflector, right? Because 3D gives you a different name, and you suddenly open up your imagination, and so people start looking at a photonic semiconductor where you have a gap, right? And you can dope your photonic crystal, and what does that mean, right? And so you can say some of those is you can guide the light in the structures and bending 90 degree, and normally in optical fiber you can't do that, and you have to make a slow turn if you use optical fibers. But if you use this kind of structure, you can have more complicated light path and metamaterials. right? And this was the first experiment where they use the split range. In fact, it's a 2D. So they show that this kind of structure, and it could have, say, negative epsilon and negative mu at the same frequency range. And it was a pretty large structure. And they did a microwave experiment and show light can indeed go the wrong way. That's what people say, light bend the wrong way, and normally against the intuition. And after that, there are a lot of structures, right? And let's look at the clocking. Well, this is not, people are not able to do that yet. It's a different way of doing it. But that's the sort of what I was explaining, right? If your light doesn't get scattered into other directions, essentially, if you're away from it, you don't look at it, there's no reflection signal you can detect. Okay, and so story is don't miss the details. Okay, some of the tiny effect, but it could be a big story.